Okay, today we're going to go over using vertex form to create a quadratic function. So, we have several points here. They've told us the distance of a nozzle, and they've measured. Imagine someone's got a hose and they're spraying water. Depending on how far the water is away from the person, this is how high it is above the ground. We're going to use each of these as a coordinate. Okay? So, the very first coordinate, when the person is holding the hose and the water is just escaping, is at 0 and 0.5. So in other words, the person is about 0.5, we'll say this is meters. Meters above the ground. That's how high the nozzle is. After 1, let's go meter away from them. After 1 meter away, it is 1.4 meters in the air. After 2 meters away, it's 2.1. 3 is 2.6. 4 is 2.9, 5 is 3 on the dot, 6 is 2.9 again, then 2.5, and 8 is 1.9. Okay? So, we can draw a curve of best fit through these points here. Do my best. That was actually pretty good. Okay? So, we know we have roughly a parabolic shape. Okay? So, this is going to be a quadratic equation. We have somewhat of a parabola. Since we're using our vertex form to solve this, what we're going to need to find is the vertex of this. What point would be considered the vertex of this equation? 5 and 3, that's right. 5 and 3 would be the vertex of this equation. Yeah. That information allows us, 5 and 3, that information allows us to actually create a quadratic model. So it's here. So we brought up a whole bunch of formulas here that deal with quadratics. We have standard, factored, and obviously vertex form is the one we're going to use. What we've discovered is the vertex, they actually replace our h and k in this formula. So let's go back to page width here. We're going to drag that formula down for our vertex form. So, since we now know the vertex of this equation, we can replace it. We know that y will be equal to, we still don't know the a value of this, x minus or plus, depending. What is our h value? Our h value is 5. So when I put it into negative, our h is going to be the number 5. Bracket squared. And then plus positive 3 goes in, so we have the number 3. So I've already found out quite a bit about this. In fact, I'm only really missing one variable. We have our a, x minus 5 squared plus 3. In order to figure out what the a value of this is going to be, what will I need to do?
Isolate.
I'll need to isolate, but I still have an x and a y.
You probably just like take one of the x's from one of the other.
Yes, I'm going to take the x and y from another coordinate. So what coordinate would you guys like to use? Let's go back up.
7 and 2, 5. 0, 0, 5.
Yeah, it's actually so much easier.
7.7 and 2.5 will be relatively easy. 0 might be quite easy, because 0 tends to eliminate a lot of things. But either will work. And you know what we'll do? We'll plug both in just to see that we get the same answer as we go through, or something relatively close. Okay. So we'll split this up. Because I'm using a line. It's not by hand. So the coordinates we're going to use are 0 and 0.5 as our x and our y. And the other coordinate was 2.5 and 7? No, I think it was 7 and 2.5.
Yeah,
Yeah, let's check. Yeah, we're going to go 2 different ways just to show you that either will solve your problem. Okay? So, this is our x and a y. Now, I want you to be aware of this. These points may give us an a that is slightly different just because we're using a curve of best fit. We're looking for an a that's relatively close. And you're going to notice it's going to be quite close. If we're using an actual equation, they would be exact no matter what. But because we took data from something, it doesn't always make a perfect shape for us. Okay? But this one, let's find out exactly what we're going to get here. So we already had our formula from before. Our y value is 0.5, so 0.5 is equal to, we're still solving for a. Our x value is 0, minus 5 squared plus 3. Our other version, y is 2.5 is equal to a. X is 7 minus 5 squared plus 3. So, first things first, let's deal with our bracket. 0.5 is equal to a. 0 minus 5 is negative 5. And what's negative 5 squared?
No.
2.5 is equal to a. 7 minus 5, 2 squared is? Okay, we did that 2 in one step there. So now we're left with 0.5 is equal to 25a plus 3, and or 2.5 is equal to 4a plus 3. Sorry. Okay. So now we got to isolate a just like Nick said. So we're going to reverse bedmass. I'm going to move the 3 in both equations to the other side. 0.5 subtract 3 gives us 25a, and 2.5 subtract 3 gives us 4a. Okay. In this one, we're going to get negative 2.5 is equal to 25a. And this one's going to be negative 0.5 is equal to 4a. We're going to bring over, on the left one, we'll bring the 25 to the other side. So negative 2.5 divided by 25 equals a. And in this one, negative 0.5 over 4 equals a. We'll use a calculator to solve both. Anyone know what the first one's going to be?
10.
Close. 0. So we get negative 0.1 is equal to a, and our other 1.5 divided by 4, 0.125. So, negative 0.125 for our other a. Now remember I said we collected data, right? That's why ours were a little different in this instance. The number was a little lower on the 7.25, and the reason I knew this would happen, I'm going to show back up here. Remember that parabolas are symmetrical, right? So, if my vertex is at 3, that's going to disappear. So if my vertex is at 5 and 3, and the point 1 to the left of it is 2.9, and the other is 2.9, I know those are symmetrical. We've gone 1 in both directions, and the heights are the same. For a parabola to work, that needs to be constant the whole way through. But in this one here, we had 3 and 2.6, and 7 and 2.5. That's a little lower, so not exactly identical in terms of being symmetrical. So I knew I would get a somewhat different a. It wouldn't be very far off. In fact, it's 2/100ths of a meter off, or well, of a factor off. We're going to round it to negative 0.1 just to make this easy. Okay?
Makes sense, because that's why it's so flat.
Exactly. It's a hose, right? So there's a lot. It's not like a line that has essentially no diameter. A hose has a diameter to it, so the measurement maybe will be a little different. Well, we've got everything we need. Our formula is y is equal to negative 0.1. Our h is still 5 squared plus 3. And that's it. We just needed the equation for this model. We found the equation, and technically we could be done. What form is this? Vertex. What if they tell us they want us in standard form?
And we would foil it.
Expand.
Yeah.
Exactly right. We would expand. So, the foiling, the same idea, we would expand. Y is equal to negative 0.1, x minus 5 times. Good.
Foil back.
So what we're doing is going from vertex to standard form. We would FOIL what's in those brackets, so we're going to be left with x squared minus 10x plus 25. Okay, I know I did that a little quick. What I did there is I did x times x gives me x squared. Negative 5 times x is negative 5, and x times negative 5 is negative 5. So essentially I had two negative 5x's. What does that become? And then negative 5 times negative 5 is positive 25. As we go down. Okay, so the next step we'll need to do is distribute this negative 0.1 to all of these. Let's move this down a little. We are going to get negative 0.1 x squared, positive 1, I think, right? So we should get, yeah, positive 1x. And this should give us negative 2.5, I believe. Plus 3. All we have to do is equate the last term on the end. Plus x. And then plus 0.5. Okay? Now, the reason I know this is right, we're in standard form. What point does standard form tell us? There's one point on a parabola. I can look at standard form and instantly know that point.
0.5.
What is that?
The y-intercept.
The y-intercept. The y-intercept, because in standard form, that means the y-intercept is when x is equal to 0. So essentially, our first two would cancel out or create zeros, correct term, and 0.5. And that's exactly what we started with when we did go through this, remember? 0 and 0.5. So I know that the standard form I created is probably quite accurate for this model. All right, just as a side note, say that I've plot data, this is going up by ones, we'll say, okay? So 2, 4, 6, 2, 4, 6, 8, 10. I want you to just take a brief look at this. Now, this might look exactly like the vertex, but the vertex actually might fall somewhere like here-ish, right? It's probably something like that. So when making a curve of best fit, you can always take their point, or sometimes, I should use a little bit of a better example. Let me fix these a little. Think of it like this, maybe. So we get another point here, then I got another point here-ish and down, okay? Because of the distance between these two here, I get the idea that the vertex falls somewhere in between here. So sometimes to make the model a little easier for myself, I might decide that this will be the vertex, which would give me a number 5 and 5, right? Much easier to work with. That's why we tend to plot the data. That way sometimes we can go, you know what, the vertex maybe falls in between. We might even get something, let's say I do it in blue. It is estimating, right? Just like the other way, and that is quite exact that way. You're right. Your A's and your vertex will be a little different, and I said they won't always be the same in these questions because we're choosing points along the data. We are estimating. Yeah, as long as they're similar, it's right. Like, say, for instance, if I did something like this, kind of obvious that we're probably going to get a vertex in between here, right? So I'm going to have to estimate a point like that. So I want you guys to keep that in mind. That's why they ask you to plot these things.